Now we can do aldehydes and ketones. We've done alcohols, thiols. We've done alkynes, alkenes, alkanes, which are different molecules, different molecule types in organic chemistry. Let's look at aldehydes and ketones. So what you're looking at here actually is acetylbenzene. This is the ring, and you have what we call a carbonyl and a CH3. So aldehydes and ketones, for example, in this molecule, will always contain carbonyl. Before we start, please make sure you take that in. Carbonyl. Aldehydes and ketones are carbonyl containing functional groups. The other carbonyl containing functional groups include carboxylic acids, esters, so that's an ester. These are carboxylic acid. That's carboxylic acid. Also amides will contain the carbonyl. Okay, you'll have a nitrogen bonded to the carbonyl. Okay, so these are common carbonyl containing compounds. Now here you have a carbon, carbonyl, carbon. So generally you have this structure. That's gonna be a ketone. Okay, for the aldehyde, like what's shown on here, okay, this molecule when drawn looks like this. Aldehyde will at least have a hydrogen bonded directly to the carbonyl, so aldehydes can take this form, or the babiest aldehyde will have two hydrogens. So you at least have one hydrogen to make an aldehyde. You at least have one hydrogen bonded to the carbonyl to make an aldehyde. So now that we know what ketones and aldehydes are, let's dig in. Remember the word carbonyl, very important. Here are examples of aldehydes. Cinnamaldehyde, thing that can be extracted from cinnamon. You have formaldehyde, which is used as a preservative of organic material like mollusks, octopi, crabs in the zoology lab. You have estrone, okay, looks like part of the hormone estrogen, and then you have testosterone, which of course is seen in male hormones, where this one must be seen in an organism. So the testosterone is a ketone. You see, you have a carbonyl bordered by two carbons. Estrone is also a ketone. Carbonyl bordered by two other carbons. Cinnamaldehyde is an aldehyde. You at least have one hydrogen bonded directly to the carbonyl. Okay. Formaldehyde is an aldehyde. You at least have a hydrogen bonded to the carbonyl. So these are common. Some examples, not the only ones. They're just some examples of ketone containing natural products, or aldehyde containing natural products. I'm calling them natural products because they're found in nature. So how do we name the aldehydes? How do we name the aldehydes and ketones? So for an aldehyde, the ending of the name will be Al. Okay. Now, for example, here you only have one carbon, so one would have called it methane. According to our reference, functional groups called alkanes, it would have been a methane, but because we are looking at an aldehyde, the suffix E is replaced by Al, so it becomes methanal. This is the common name in parentheses formaldehyde, and like I said, that's used to preserve organic fleshy material in the zoo lab. Okay, so like preserving crabs, mollusks, and organs in anatomy lab and all that. This one has 2 carbons, so we give it F. If it were an alkane, it would have been ethane. So we take the E, replace it with Al. You end up with the name ethanal because it's an aldehyde. Common name acetaldehyde. This one has 3 carbons, or we start numbering from the carbonyl. Always for the aldehyde you number from the carbonyl because it will always be at the end of the chain. So prioritize the carbon of the carbonyl. So you have 3 carbons, and it would have been propane, but because it's an aldehyde, the E is dropped, replaced with Al, so the name becomes propanal. Common name propanaldehyde for common man. This one has 4 carbons, so it should have been called butane. We drop the E, we replace with Al, becomes butanal, and it's normal butylaldehyde because it's straight chain, it's not branch like to give you sec-butyl or tat-butyl. Okay, so the UPAC names can also be obtained for other systems. For example, if the aldehyde is branched, like I said, prioritize the carbonyl of the aldehyde, whether it's on the left or right. Also do the same for the carbonyl of the ketone. Give that carbonyl carbon the lowest number possible. So numbering, you get 4 carbons on the longest chain, which means this becomes a substituent and it's on the 3rd carbon, so it's 3-methyl butanal. Here we have a double bond, we have the carbonyl, so again we prioritize the carbonyl over the double bond. The double bond is on position 3, so it's 3, it should have been 3-butene, but it's an aldehyde, so we drop the E, we replace it with Al, so the name becomes 3-butenal. Again, prioritize the position of the carbonyl 1, 2, 3. OHS become your substituents, they're on carbon 2 and 3, so we do 2, 3, di. We use the hyphen to separate alphabets from numbers. Use comma to separate the numbers. So 2,3-dihydroxy. OH as a substituent is called a hydroxyl group. So when it's within the name becomes hydroxy. 2,3-dihydroxy, 3 carbons, so it's prop. It would have been propane, but because an aldehyde we call it propanal. The E is dropped, replaced with Al. What of when they are rings? This is different. For rings, we have to include the word carbaldehyde if the ring is not aromatic. Okay, so like this one right here, it's a regular alkane ring, so we'll have to use carbaldehyde. It's not aromatic like benzene is. So if you cut like at that point, then the ring becomes a substituent. That's the procedure you follow. Substituent. The ring becomes a substituent. Let me write it here. The ring becomes a substituent. It's a 5-membered ring, so it would have been cyclopentane. But because it's a substituent, so it becomes it's taken as the first name of the first part of the name, so it's cyclopentane, not cyclopentyl like we did in alkanes, not like cyclopentyl, like taking it to be part of the longest chain. No, we do name it differently from the alkane. So it's cyclopentane, carbaldehyde. Okay. Now we are just calling it carbaldehyde because this is an aldehyde. So you have the cyclopentane part, the aldehyde part, so it's cyclopentane carbaldehyde, because I told you we have to include this name whenever you have a ring. So you just take the regular name of the ring and then add carbaldehyde. The common name would be formal cyclopentane, because this group right here has a common name, formal group, which means an aldehyde. It's another name for aldehyde, word for aldehyde. Now this part right here is a benzene. This part is an aldehyde, so the common name will be benzene carbaldehyde. But now when it comes to the UPAC name, we'll just call it benzaldehyde because this is aromatic. Whenever you have an aldehyde, that's an aldehyde. If you have an aldehyde and an OH, the name will be salicylaldehyde because that comes from salicylic acid. Alternatively, you would take that as a branch, okay, and that's an aldehyde, right? This is an aldehyde part, and then of course this would be the benzene part. That's the benzene part. So you have benzene carbaldehyde because again it's a ring, but then the OH is on the second carbon, so 2-hydroxy benzene carbaldehyde. That will be for the common name. For the UPAC name, it will be salicylaldehyde because it comes from salicylic acid. So, and so forth and so forth. So if I'll give you this structure right here, okay, let's say you have a metal. So this will be carbon 1, this will be carbon 2. You don't start numbering from this carbonyl. So the name here will be 2-methyl cyclohexane, right? And then carbaldehyde. Okay, so that will be the name. If you have this ring with an aldehyde on it, so this part is cyclobutane, so the name will be cyclobutane carbaldehyde. Okay. Okay. What of the ketones? So ketones, you'll take your let's say you'll take your alkane name and then replace the E with ONE. So it will be alkanon. So for example, here you have 1, 2, 3. We don't start numbering on the carbonyl because it's right in the middle of the molecule. We just have to make sure that this number, the number given to the carbon is the least possible, numbering from right or left. So you have the carbonyl on the second carbon. So this name here would have been 2-propanone. And because you don't have any option anyway to put the carbonyl somewhere else to get still a ketone, then it's okay to just call it propanol without specifying the position, because if the carbonyl is at either end, it becomes an aldehyde. That is the name of your nail polish remover called acetone. Acetone is used as a solvent or some organic synthesis reactions, for example, to make isopropanol when it's reduced. Okay, again, prioritize your carbonyl position. You don't want to number from the right, because if you do so, the carbonyl will have a 3 instead of the 2. So this is the correct numbering system from the left. Here, the name is 2-butanol because the carbonyl is on the second carbon. Common name is ethyl methyl ketone. Why is it ethyl methyl ketone? Here's the reason why. If you cut this side, you get an ethyl. If you cut this side, you get a methyl. There's a CH3 right here. So it's following alphabet, E comes before M. So ethyl, methyl, and it's a ketone. That would be the common name. But the UPAC name is what I insist on. Here, the carbonyl is on the third carbon. You have 5 carbons, so it's 3-pentanone. Other is called diethyl ketone because if you cut this side, you get an ethyl. There's 2 carbons. If you cut this side, you have 2 carbons, which is an ethyl. So it's ethyl, ethyl. So we say diethyl, and then it's a ketone, diethyl ketone. Here, the carbon is sitting on the ring. You have 6 carbons in the ring. So it's cyclohexane. Cyclohexane. You drop the E, add O-N-E. So it's cyclohexanone. Prioritize the carbonyl 1, 2. So this becomes a substituent. It's a methyl on the second carbon. So it's 2-methyl. 5 carbons. So it's cyclopentane. And then because a ketone, replace the E with O-N-E instead of cyclopentane, becomes cyclopentanone. Here you prioritize the carbonyl over the double bond. So start numbering from the side that gives the carbonyl the least number possible. You don't want to start from the left in this case because the carbonyl will get a 3. So this is the right numbering. So you get the double bond starting from sp2 carbon number 3. So it's 3-butene. The longest chain would have been 3-butene. But because the ketone, drop the E, add O-N-E, ketone, ketone. That's where the O-N-E comes from. So we specify the position of the carbonyl, which is carbon 2. We put it just before the O-N-E because that specifies the on part where the double bond of the carbonyl is. These 3 specify the position of the alkene. So it's 3-butene. Drop the E, add O-N-E, but you have to specify the position of the O-N-E, position of the carbonyl of the ketone. So it's on second position. So 2 on. This is just acetophenone like we had on the first slide. Okay. Otherwise, you have a phenol group. When benzene is a substituent, it's called a phenol. Okay. You have a phenol group. You have a methyl group. Read your alphabets. M comes before P. So it's methylphenylketone for the common name. This right here is UPAC. Okay, you have phenol on both sides, so it's diphenylketone, otherwise called benzophenone. And then you have cyclopropyl on both sides. There are 3 carbons in the ring, cyclopropyl, so it's dicyclopropylketone. So for hexanal, you have 6 carbons. 1, 2, 3, 4, 5, 6. The 6th carbon should have a hydrogen on it because it's an aldehyde with Al. Orthochlorobenzaldehyde. How does benzaldehyde look like? Benzaldehyde looks like this. You can put the aldehyde on whichever carbon. That's benzaldehyde. And it has a chlorine on ortho position. So this is the meta position. This is the ortho position. This is the para position. So that should be the structure for this. What's the structure of isopropyl methyl ketone? I'm going to draw it this way. Isopropyl looks like that. Okay, so that's an isopropyl. a ketone has a carbonyl between two carbons, and then on the other side I have a CH3, right? So that's the structure of isopropyl methyl ketone, and that will be a common name. It's not UPAC. 4-pentanone. So first, draw the 7-carbon chain. 1, 2, 3, 4, 5, 6, 7. The O and E is on fourth position. 1, 2, 3, 4. So it's right there. 1, 2, 3, 4. It's right there. So that will be the answer for C. We've done those examples. I think you're satisfied. All right. So I insist both aldehydes and ketones will contain a carbonyl group, where R might be a hydrogen, or both of them could be carbons, or one could be a carbon, the other a hydrogen. So both of them could be carbon containing groups, or one would be a carbon, one would be an hydrogen, or both of them could be hydrogen. So in these cases, you'll be looking at an aldehyde. In the first case, you'll be looking at a ketone. Okay. The R groups could be alkyl groups. Double bond alkyl groups, we call them alkenyls, for example. If that's a substituent to the carbonyl, that's an alkenyl because there's an alkene in the alkyl group. Or alkynyl, where probably you have a triple bond to a carbon containing a carbonyl. Okay. Or aromatic, if it's, let's say, for example, a benzene ring attached to the carbonyl, that's aromatic. So R1 and R2 could be anything, could be carbon containing groups, alkyl, alkenyl, alkynyl, or aromatic groups, or both of them could be hydrogens, or one could be a hydrogen, the other one could be a carbon containing chain. So what are the physical properties of aldehydes and ketones? Obviously, looking at boiling point, which is one of physical property, one will have to consider intermolecular forces of attraction, what I call IMFs, intermolecular force. So you bring two alkanes together. You bring two alkanes together, you're gonna get weak intermolecular forces. We call them weak dispersion forces, or weak van der Waals forces, or London forces. All those refer to the same thing. They're weak, the boiling point will be low. Remember, for aldehydes, okay, you have carbonyl. Oxygen is more electronegative, so dipole moments will point towards oxygen. This carbon is partially positive. If you bring and align the second molecule of the aldehyde, then you expect that this partially positive carbon of one aldehyde will be attracted to the partially negative oxygen of the other aldehyde. Both of them have dipole moments, so the IMF will be called dipole-dipole because both of them have dipole. Dipole-dipole intermolecular forces. So similarly, that's gonna happen here. Still, the dipole-dipole IMFs. For alcohols, oxygen is more electronegative, so it will be partially negative. Hydrogen will be partially positive. Okay. So again, these dipole moments. So bring another alcohol. The oxygen here is partially negative. It has lone pairs. It's gonna be attracted to the partially positive hydrogen. The intermolecular force in there is hydrogen bonding. Now, you know hydrogen bonding, according to chapter 1, is stronger than dipole-dipole. Dipole-dipole is stronger than London dispersion forces. That's why alcohols will have a higher boiling point than their corresponding aldehydes. See, 3 carbon, 3 carbon, and of course these two guys will have higher boiling points than alkanes. For example, here we have butane. Smaller compounds are soluble in water. Why? Because again, there's a possibility of hydrogen bonding. Remember I said oxygen is partially negative for the aldehyde. Okay, so if you have water where the hydrogen is partially positive, all you're gonna get here hydrogen bonding, intermolecular force. It's because of hydrogen bonding that small aldehydes and ketones will be soluble in water. In fact, acetone is very soluble in water. It's a ketone, yes, but it's small, only 3 carbons. Okay, so common aldehydes. The first one is formaldehyde. How do you make it? You make it by oxidation. Remember how we defined oxidation, removal of hydrogens, right? So take your CH3 and we're gonna write it like this. Take your CH3 and lose 2 hydrogens from this, one from the CH3, one from the oxygen, and then create a double bond. You're gonna get here. You're gonna get formaldehyde. Okay, that's formaldehyde. You lost 2 hydrogens. Remember we defined oxidation as increase in oxidation number. We also defined it as addition of oxygen. We defined it as loss of electrons. Of course, I remember giving you this acronym. Oil rig, oxidation is loss. Oxidation is loss. Reduction is gain. So loss of electrons is oxidation. Loss of hydrogens is oxidation. So you're losing hydrogen gas. There's a loss. From methanol, you're losing 2 hydrogens. This guy circled that loss as hydrogen gas. Make a double bond in between, you get methanol. Usually done in silver at extremely high temperature. What about a 2-carbon aldehyde? It's still gonna be oxidation because now in this case you are adding oxygen according to one of our definitions. We use palladium copper alloy or combination at high temperature. We also use molecular oxygen. You start with 2 of these, which means 2 equivalents. So probably you have this as 1, this as 2. That's what these 2 means, 2 equivalents. You get 2 equivalents of ethanol, otherwise called acetaldehyde, which is used as a starting material for chemicals and to make acetic acid. So it's made by what we call the worker process. So this is the worker process still that's used to make propanol, the acetone, otherwise labeled 2-propanol because the carbonyl is on the second carbon, otherwise called acetone, nail polish remover. So just like we did for ethene, oxidizing it to the aldehyde ethanol, we do the same thing for making acetone. So in this case you're gonna get acetone. So there's a problem here. I'm gonna modify. Let's see, do we need to modify? No, we don't need to modify. It's okay. So we get to use worker process to make acetone. It's just oxidation. You're adding an oxygen. So again, 2 equivalents of propene converted to 2 equivalents of propanol. You can also make it from isopropylbenzene. Remember, this group is isopropyl, and the bottom part is a benzene, of course. So you can cleave this part by oxidation, but it usually goes through a radical mechanism beyond your scope, and then add sulfuric acid in a process that we call workup. So this part will fall off, that will fall off, so you're gonna get acetone. So you see how you have 3 carbons, 1, 2, 3. That's the part that makes the acetone through what we call benzylic carbon oxidation. That's a benzylic carbon oxidation. So you can also oxidize isopropanol, otherwise called 2-propanol. This is a sign for oxidation. Remember we talked about alcohols in chapter 7. I'm not doing chapter 8. So you can use pyridinium chlorochromate or you can use Jones reagent. PCC is mild. Jones reagent is a strong oxidant. Both of them will oxidize. Both of them will oxidize the secondary alcohol to a ketone, because always secondary alcohols are oxidized to ketones. And this happens to be your acetone or 2-propanol or just propanol. That's the third way you can make acetone. Okay. Now, if you have primary alcohol and just use PCC, you'll stop here at the aldehyde. Okay. But if you have the primary alcohol and use Jones reagent, okay, it goes all the way to the carboxylic acid. So it will go all the way. Now, going back from carboxylic acid to aldehyde is reduction. That's what the R means. Remember, the O means oxidation. They are reducing agents like lithium aluminum hydride, or another one that we call dibol. We'll talk about them if we discuss the chapter on carboxylic acid and derivatives. So same lithium aluminum hydride can be used here, or dibol, or even another one called sodium borohydride. So going backward is reduction, they are going forward is oxidation. Depending on the strength, if it's mild, stops at the aldehyde. If it's strong, like Jones reagent, goes all the way to the carboxylic acid. That's how primary alcohols behave. Remember, tertiary alcohols are never oxidized. No reaction for tertiary alcohols, never oxidized. The reason being, there's no hydrogen here. You have to have a hydrogen that you can remove. That's one of the definition of oxidation. So again, that's Jones reagent as discussed in chapter 7. So I expect this is primary alcohol because you only have one R group. I expect it to be oxidized all the way to the carboxyl group because this oxidizing agent is very strong. This is a secondary alcohol because I see two R groups. That's one of the R groups, this is the other R group. So it's secondary. Oxidized secondary alcohols, you always get a ketone. Where the OHs make a carbonyl. If it's PCC, PCC is mild. So the primary alcohol will be only oxidized to an aldehyde. Okay, remember what I said. For tertiary alcohols, no oxidation because this carbon right here has no hydrogen. You have to have at least a hydrogen. You see how this carbon has at least a hydrogen for primary, and for secondary you do have a hydrogen here, so oxidation can happen. Again, these are primary, you have two hydrogens, so oxidation can happen. But for the tertiary, there's no hydrogen, the oxidation will not happen. Okay. Another way to make ketones is by what we did in, I think, chapter 4, Friedel-Crafts acylation. I won't go much into detail on it, but just remember that the benzene was used as a nucleophile, and this part gives you the electrophile. After the Cl falls off, you get an electrophile. The nucleophile will attack the electrophile. So you simply click in the benzene to this electrophile after Cl falls off. You get what we call acetobenzene. Depends on what you have here. It could be a CH3, it could be CH2, CH3, it could be a ring. That R group could be any carbon containing group. Regardless of that, we have a ketone. because we do have a carbon here and a carbon there bordering a carbonyl, and that's the case for ketones. Alkynes can be oxidized to ketones by a process that we call oxymercuration, demercuration, like you're adding mercury and then taking it out reaction. Okay, so it's oxymercuration, demercuration, oxidation reaction. So basically what happens is whenever you're adding your water, you'll get one pi bond gone, and then the OH will be attached by Markovnikov addition. So OH goes where there's more hydrogens. You see here there's one hydrogen, here there's no hydrogen. So OH goes where there's less hydrogen, sorry. The OH goes where there's less hydrogens, the hydrogen goes where there's more hydrogens. So there's no hydrogen here, there's one hydrogen here, so the hydrogen part of water, because water is just H and OH, so the hydrogen part of water ends up where there's more, which is this side. So now we have a CH2. OH adds across on the side where there's less, which is on this carbon. You get what we call an enol, and then that enol does what we call tautomerism. So let me explain what that is. So you have an OH and then you have a CH2. You have a pi bond. So what happens is that this pi bond opens up, picking up the hydrogen. This bond makes a carbonyl. So you end up with a double bond, which is a carbonyl, and then this CH2 becomes CH3 because the pi was used to steal that hydrogen. And this molecule right here is that molecule. This process of arrow pushing is what we call tautomerism. It's just a fancy rearrangement. Okay, so that's how you can convert alkynes to ketones by oxymercuration. We're using mercury, so it's oxymercuration. It's oxidation because you added an oxygen. Aldehydes and ketones happen a lot in nature. We talked about cinnamaldehyde, we talked about testosterone and all other hormone-looking molecules. They are grouped together because they have similar properties. Why? The reason is the presence of the carbonyl. The carbonyl has different reactivity. Key point about the carbon is that you have dipole moments. Electron density is much on oxygen, so that will be partially negative than the carbon, which is partially positive. So you can imagine if you have a nucleophile, the nucleophile can attack that carbon, the pi bond will open because nucleophile is negatively charged. This carbon is positively charged. Opposite charges attract. That's how you can attack a carbon for it to open up. That happens for both aldehydes and ketones. That's why they are classified together or grouped together, because they possess a carbonyl group which tend to react in the same way. So like I said, dipole moments will make oxygen partially negative, the carbon partially positive, and this is the case of a ketone. Okay, so the covalent bond here is polar and covalent because we have the partial charges. So which means one can draw resonances, so you can push the electrons towards the electronegative oxygen, because again dipole moments points towards the oxygen. That will render this carbon one bond less, so it's just gonna have one formal charge. If you doubt, formal charge equals to number of valent electrons, and carbon is 4, minus non-bonding pairs, there's none, minus number of bonds, there's 3, so you get plus 1, which is that charge. For oxygen, you have 3 lone pairs. Here you have 2 lone pairs. After donating the 2 electrons from the pi bond, it becomes 3 lone pairs. So if you are to do the formal charge of this oxygen, will be equal to number of valence electrons on oxygen on the periodic table is 6, minus how many non-bonding electrons? 6, and then minus number of bonds 1, so it's -1. That's where this negative comes from. So basically after this resonance you get O minus and a plus charge there. You see there's a plus character on this carbon, and that's why, like I said, the nucleophile will want to attack it. Now this process is not possible. This is not possible, does not happen. The reason being, oxygen is more electronegative than carbon. You don't push the arrows the other way. The electrons want to go to the electronegative element, because electronegativity is the affinity for electrons of an element, of an atom, of an element. So this is wrong arrow pushing. This is the correct resonance across the carbonyl. So like I said again, nucleophiles with their lone pairs will want to attack this carbon, because like we drew the resonance, you found that this carbon is positively charged, opposite charges attract. Okay, but in another way, looking at electrophiles, if you have an electrophile, then the lone pair will be used to attack the electrophile. So specifically, let's say you have H+, then the oxygen of the carbonyl will be used as a nucleophile this time around to attack the electrophile. That's the specific example for this situation. So this will be used as a nucleophile. The electrophile is attacked. The electrophile example is H plus a proton, and the oxygen will use its lone pair to attack it. So oxygen takes the role of a nucleophile, alternatively takes the role of a base, because bases are proton acceptors. Because after this very reaction, you will have a lone pair, you will have a hydrogen and a positive charge on oxygen. So the oxygen accepted a proton as seen in the product here. So the carbonyl can play the role of a base or nucleophile because it's attacking an electrophile. So generally, if you use a nucleophile, the arrow should start from the lone pair. You attack the partially positive carbon. This opens up. This is almost an SN2 reaction type because it's concerted. And you can attack from the top or bottom. So if you attack from the top, then H and R will be pushed down. Now you started with an sp2 center, you end up with sp3 center. There are four electron domains, 1 2 3 4 bonds. Here there are 3 electron domains, the double bond and the 2 single bonds. So it's sp2 here, sp3, and we know the molecular geometry of sp3 is tetrahedral. So it's a tetrahedral alkoxide because you have a negative charge on oxygen bond bound to carbon, which are usually strong bases. So if you add water, the alkoxide will play the role of a base, just like I explained here. Okay, so the oxygen will use its lone pair to take out this hydrogen, and that falls off. So now your alkoxide is now an alcohol product. Of course, the other part of water will get lost as OH minus, which is possible because this base is stronger than OH minus. So in this OH, this OH will be taken as a good leaving group in this case, because you're in the presence of a very strong other basic molecule. So anyway, you'll have converted your ketone or aldehyde. In this case, actually this is an aldehyde because you have a hydrogen. You'll have converted your aldehyde to an alcohol. Okay? So again, oxygen can use its lone pair to accept a proton. So this aldehyde will take the role of a base because it's accepting a proton. What's wrong with my pen? Let's clean up. So it's accepting a proton. So you have a formal charge. I did the math where you can do resonances. So this carbon right here becomes partially positive. That's an alcohol. And then the nucleophile, starting from the lone pair, can come to attack the positive center. You end up with an alcohol. So you can convert an aldehyde to an alcohol either in acidic medium or right here in basic medium, because this is negatively charged, so we are in basic medium. Okay, See how you're forming a base here, and alkoxide is a strong base. So this is basic medium reduction condition from aldehyde to alcohol. This is acidic medium reduction reaction of the aldehyde to the alcohol. Okay, so the reason why you want to do step number 1 is once you have a positive charge on oxygen, it's quicker to make a positive charge on the carbon. So there's an enhancement of the plus character on the carbon to be attacked by the nucleophile in the next step. So the product is the same, but the resonance structure too, this structure right here, enhances the attack of the nucleophile as the carbon now has a true formal charge. Okay. Alright. So what we have done here is adding a nucleophile. So you added a nucleophile, so it's nucleophilic addition. You added a nucleophile. So you added a nucleophile, so again it's nucleophilic addition. These nucleophilic additions using nucleophiles can go either back and forward. Okay? Those that add reversibly are good leaving groups, which are conjugate bases of strong acid. For example, Cl minus or Br minus. So if you add such nucleophiles, they're gonna either break apart or break apart or attack. So it's reversible. The reaction can go forward or backward. What I mean is this: if you have, let's say, an aldehyde, and then we are adding Cl minus. So if Cl minus attacks here and this opens up, what do you get? You're gonna get your hydrogen, your O minus after the pi bond open, and then you're gonna get your Cl attached onto it. Let me remove the charge. So the problem is this: this Cl right here is a good leaving group. This oxygen can decide to reverse the process by making back the carbonyl, and this falls off. That's the reversibility we are talking about, in which case you will get back your starting material which has a carbonyl. Okay, you get your starting material which has a carbonyl, so which takes you back to where you started. So that's reversible. Those that do irreversible are poor leaving groups. For example, OH, because if OH leaves, it makes a strong base. Good leaving groups must make weak bases. For example, here, once you make back your carbonyl and Cl leaves, you get Cl minus, which is highly electronegative, and it's a good leaving group. But here, if you attack the carbonyl and this opens up, you end up with your alcohol. You end up with your alkoxide, sorry. So now the OH is attached. So this oxygen cannot and should not make back its double bond for this to leave, because OH is a poor leaving group compared to Cl minus, which can do reversible. So in this case, it's irreversible. I only show one arrow. Here it's reversible, so I show both back and forth, because Cl is a good leaving group, even though it's a nucleophile. So you want to use strong nucleophiles for it to be irreversible. Cl is not a strong nucleophile. Okay, so again, why are aldehydes more reactive than ketones? One should compare two things. The first thing to compare is, suppose you have resonance, then you're gonna have a plus charge on here and the CH3. So the CH3, or the R group, so to speak, will donate electrons, quenching this positive charge. Alright, so now compare that with a ketone that has two R groups or two CH3s. Then you have two groups quenching the partial positive character. Alternatively, if I want to show the resonance, then this would be the resonance. So assume you have two CH3s. Now you have two things killing the plus character. For nucleophilic reaction to happen, you want the plus character to stay. So which of these two has the most plus character on the carbon? It has to be the aldehyde because only one group is killing it. You want it to be around for the nucleophile to attack that carbon as we did here. You want the plus character here for the nucleophile to attack. So if the plus character is quenched, if the plus character is quenched, as in what we see in ketone, if the plus character is quenched, then this carbon right here is has less of a plus character, and the nucleophile is less likely to attack it. So point number one, stability of the carbocation. So ketones are more stable because they have at least two carbon-containing alkyl groups quenching the plus character. Because they are more stable, they are less reactive than aldehydes. The second reason is sterics or crowding. So if you have two R groups down here and the nucleophile wants to come in, it's going to have trouble coming in because there's no much space in between. But for an aldehyde, let's take this aldehyde for example, where you have hydrogens, not carbons. Those hydrogens are not obstructing anything the nucleophile would attack. So that's what we call steric hindrance. So aldehyde is less hindered at the backside. Remember we said this reaction tends to be similar to SN2. SN2 doesn't like sterics, so the nucleophile can easily access that carbon to attack by SN2 as compared here. For example, if you look at acetone, replacing these hydrogens with methyl groups. These methyl groups will obstruct the nucleophile from accessing that carbon to attack it. So whether you have one hydrogen on a carbon or you have two hydrogens, the aldehydes, these aldehydes are more reactive than the ketones because the backside is accessible by the nucleophile. That's the steric interaction. The first one we talked about stability. Two R groups will stabilize the carbon of the carbonyl, quenching the plus character. Then the nucleophile is not much attracted to that carbon because that positive charge is not there as much. But with aldehyde, there's only one stabilization, so the plus character is more on here. So the nucleophile, which is having a lot of electrons, will be attracted more to that one, to that carbon in the case of aldehydes. Okay, so ketones will be less reactive than aldehydes because ketones have less of the plus character on the carbon of the carbonyl compared to the aldehydes. Again, for sterics, ketone is hindered on the backside. Okay, so this backside is hindered because you have the R groups compared to aldehydes where at least you have a baby hydrogen which does not hinder the nucleophile from coming in. Okay. So reactions of aldehydes and ketones. The following pages will deal with the nucleophilic addition reactions to carbonyl groups based on the nature of the nucleophile. So just to remind you, we are attacking, so whether you have a ketone or an aldehyde where this will be CC or CH or HH, in this case you have aldehyde, and the first case you have ketone where the R groups are CCs. Whether you have ketones or aldehydes, we are attacking this carbon again because of dipole moments that makes the carbon partially positively charged. So the nucleophile should attack here. So in the slides moving forward, we will be dealing with the nucleophilic addition reactions to carbonyl groups based on the nature of the nucleophile. Is the nucleophile negatively charged? Is the nucleophile neutral? Is the nucleophile negatively charged? Is the nucleophile negatively charged? Is the nucleophile neutral? Okay. So if you have water or an alcohol, it doesn't matter. Water or alcohol, these are neutral. Okay. So whenever you attack the partially positive charge, the oxygen can open up picking up a proton. Remember again, it's SN2 type. So the immediate product you'll get is this. Okay, let me choose a different color. So your alcohol that attacked will be here. So this is the part I'm trying to draw. So you'll visually see it. So your alcohol added, you used one lone pair, so that's why the oxygen has a plus charge. Now, from here to here, you want to neutralize this plus charge, so you're gonna bring in another alcohol to do what we call proton transfer. I've talked about this step so many times. Organic molecules don't like being charged, so you simply use 2 electrons from this hydrogen that's stolen by another alcohol to neutralize the O+. Now your oxygen, this oxygen has 2 lone pairs and it's neutral. So notice that you have an OH and an OR group. This could as well be OCH3. So we have where you have an OH and an OR group, that's called Hemiacetal. That's this part. If both of them, if these guys are taken to one more step of addition, like we did here, you're gonna end up with 2 OR groups. Again, I repeat, you end up with 2 OR groups. Whenever you have 2 OR groups attached to that carbon, that's called acetal, which is this part here. So hemi means half. Okay, so half the acetal. Where you have 2 OR groups, this could be OCH3, OCH3, or OET, OET, or an oxygen to a ring, an oxygen to a ring. It doesn't matter. Whenever you have 2 OR groups, that's called an acetal. Where you have 1 OH and 1 OR, that's half the acetal, so it's hemiacetal. We will have to use acid catalyst. You see how we are using acid catalyst? Because these 2 guys are neutral. They are weak nucleophiles. Strong nucleophiles will be negatively charged. So if they're weak nucleophiles, we have to activate the carbonyl to make it a strong electrophile so that the weak nucleophile will attack the activated electrophile. Okay? Sounds like too much chemistry, but let's look at the mechanism. So like I said, whenever you are using alcohols or water, those are neutral. They are neutral nucleophiles. And we did this in an earlier chapter, I think chapter 6. We said neutral nucleophiles are weak. So before they come into attack, we usually use an acid catalyst. We use an acid catalyst to at least make this carbon here even super positively charged so that the weak nucleophile can come and attack it. So we use the carbonyl as a base, alternative as a nucleophile to accept a hydrogen, because bases are proton acceptors. So you get this structure. Now because oxygen is positively charged, the dipole moments here are even greater. Electrons are pulled even much towards the oxygen, then this carbon becomes even more partially positive, and now the weak nucleophile has a chance to attack the carbonyl. You attack it, and then this opens up. Okay, so after that, when you attack the carbonyl and the pi bond opens up, this becomes OH. This part to the left, this part is actually the alcohol that added, and the oxygen will have a plus charge because now the oxygen only has one lone pair. You can do the formal charges if you want. Now, like I said, alcohols, organic molecules don't like carrying charges, so you can use another alcohol to do the proton transfer to steal this hydrogen and then use this bond, donate it to the oxygen. So the alcohol here is used as a base. Proton transfer. Guess why it's called proton transfer? Because you're transferring a proton from this molecule to this molecule. So that's what this means. You lose the H plus. You lose, the subtraction here means lose the H plus. So you end up with an OR group, and of course we already made our OH. You have OH, you have OR. This is half the acetal, so it's hemiacetal. So that's how you make your hemiacetal. The alcohol that took out the hydrogen simply forms a byproduct which is not of our interest, the alkoxonium. Okay. The hemiacetal that's formed here can be taken to one more step. So please turn over. We are continuing with this reaction. So again, we make OH a good leaving group by activating it with an acid catalyst. We are going towards making the full acetal. Remember, this is hemiacetal. So OH is activated. We don't want it to leave as a OH minus. We would rather have it leave as H2O. That's why we're activating it to leave as water, which is a weak base. Water is a weak base. OH minus is a strong base. My pen is acting up. Water is a weak base. OH minus is a strong base. We said good leaving groups must leave as weak bases. So we first modify the OH and make it look like water. So we activate it, use a lone pair. This is just acid-base reaction. Use OH as a base to accept the proton. You get this alkoxonium. Now the OH2 can leave as water, you see. Lost as H2O. So the OH is now lost as H2O within the structure of H2O. You lose a bond from this carbon, so it becomes a carbocation. But now, remember, this oxygen has a lone pair. So that lone pair can go inwards. The lone pair can be used to make a pi bond right here. So you'll be left with one lone pair and a plus charge, of course, right? Now, these are resonance structures of what happens after water is lost. Now take this structure, which has a plus on the carbon, okay? Take this structure and attack it with a second alcohol. Remember where we started? We used an alcohol as a nucleophile, right? To make the hemiacetal. So we are using a second equivalent. We are using a second equivalent of the alcohol to attack the positive center. Again, the arrow should start from the lone pair. To attack the positive center, you end up with this. And I'll tell you again, molecules don't like carrying the charge. So you do a proton transfer with another molecule of an alcohol, and then take out that hydrogen, use the 2 electrons that make this bond to neutralize the oxygen. Now you have OR, OR. So where you have 2 ORs, that's called an acetal. Right? So overall, hemiacetals can go through one more step to be converted to an acetal. The mechanism is SN1 because we've gone through carbocation intermediates. Okay, you notice that we went through carbocation intermediates. So it's SN1 here. It's SN1 here. We are attacking a carbocation. These are carbocation. and then it's also, let's see, no, in this place in making the hemiacetal actually is SN2. In making the acetal itself is SN1. Okay, hemiacetal here SN2 because you see how we are tacking and opening, the reaction is concerted at this point. So it's SN2 to make the hemiacetal. But if you take your hemiacetal to one more step reaction, you have to go to SN1 because we went through carbocation intermediate. All right. So we'll continue from here.